Greetings to all. I am Arul Kumar, working as Assistant Professor in Department of Mechatronics Engineering, Kamaraj College of Engineering Technology. In this video lecture, we are going to discuss about uncontrolled rectifiers. The structure of the presentation is what do you mean by rectifier, then working principle of rectifier, then types of rectifier, then the performance comparison of rectifiers. What is meant by rectifiers? Rectifiers is a device which converts alternating current into direct current. That means AC quantity into DC quantity. That process of converting AC into DC is called as rectification. The types of uncontrolled rectifiers are, the first one is half wave rectifier, then the second one is full wave rectifier, then the third one is bridge rectifier. First we are going to discuss about half wave rectifier. First we are going to discuss about half wave rectifier. The half wave rectifier circuit comprises of the input source side, then transformer primary side and then secondary side, then the PN junction diode. This is the anode terminal and this is the cathode terminal. Then the load. This is the circuit components of the rectifier, giving positive to the anode and giving negative to the cathode is called as forward biasing. Suppose if we are giving negative to the anode and positive to the cathode, means it is called as reverse bias. During the forward bias, the diode will be in conduction state. During the reverse bias, the diode will be in blacking state. This property is very much used in rectifier circuit. The working principle is comprises of two phase. The first phase is positive half cycle, then the second one is negative half cycle. During the positive half cycle, here the positive is there, here negative. So the anode is positive, then cathode is negative. So the diode is in forward bias. So it allows the positive half cycle to the load side. Then during the negative half cycle, this terminal is become, instead of plus, here minus and here plus. Here the diode is in reverse bias. So in reverse bias it will be in blacking state. So blacking state, it doesn't allow the input signal. So from positive half cycle it starts conducting. In the reverse bias it is in blacking state, therefore there is no output. So it allows only the positive half cycle to the output. This is called a half wave rectifier. Then we are going to discuss about the half wave rectifier in reverse bias. In reverse bias, the diode is in blacking state. Then reverse half cycle, there is no output. The diode is in blacking state, so the output is 0. During the reverse bias, the output is 0. Since the diode is in blacking state, therefore the output is 0. From the name itself, it clearly indicates during only one half cycle the diode will conduct. During the negative half cycle, the diode is in blacking state. That's why it is called as half wave rectifier. The limitations of half wave rectifiers are the ripple content. What do you mean by ripple content? The ripple content means we are using a rectifier for converting AC into DC, but the AC signals present in the DC side is called as ripple factor. So we need to eliminate that ripple. The ripple factor is 121%. Ripple factor is 121% for half wave rectifier. Then transformer utilization factor. Here we are having a transformer. This transformer utilization factor TUF is only 28%. It is also another one limitation. So these are, and then output voltage level. Output voltage VM is equal to output voltage VDC is equal to VM by pi. So lower output voltage. Then efficiency, we are having an efficiency is equal to 40.6% only. These are all the limitations of half wave rectifier. So to nullify the limitations of half wave rectifier, here we are moving towards full wave rectifier. Full wave rectifier, we are having two combinations. One is full wave rectifier with the center typed transformer, and another one is full wave rectifier with the bridge configuration. So first we are going to discuss about full wave rectifier with the center typed configuration. In center typed configuration, in the secondary side we are having three terminals. This is the ground terminal, it acts like a zero potential, and here we are having an positive, and then here we are having a negative. During the positive half cycle, here we are having an positive, here we are having a negative. During the negative half cycle, here we are having a negative, here we are having a positive, and then we are having two diodes, the diodes D1 and then D2. So during positive off cycle, the working of full wave rectifier is split into two modes. The first one is positive off cycle. During positive off cycle, the diode is in forward bias. The diode D1 is forward bias. Here, during the positive off cycle, this terminal is plus and this terminal is minus. So D1 is in forward bias, plus minus. Therefore, the diode is in on state. Just it follows the input supply. Similarly, D2, if you are looking about D2, for anode, here we are giving an minus. For cathode, here we are giving an, so for anode, here we are giving an minus. Therefore, the D2 is in blacking state. So the D2 doesn't conduct. So the output voltage follow this path. This is the current flow path of center tapped transformer during positive off cycle. Next we are going to see the negative off cycle operation of. During the negative off cycle, this terminal is minus and this terminal is plus. So diode D2 is become forward bias. D1 will become reverse bias. So it will be in blacking state and it will be in on state. So the current flow is following this path. So across the load we are having an plus and minus. During two quadrant we are having an unidirectional output. This will be repeated continuously. The advantages of full wave rectifiers is, the first one is the output is continuous output. We are having an output during positive off cycle and we are having an output during negative off cycle also. Then the output voltage VDC is equal to 2 Vm by pi. Then transformer utilization factor TUF will be increased to 68%. Then the efficiency is increased to 81.2%. The ripple factor tau is also reduced. So these are all the advantages of full wave rectifier with the center tapped transformer. The only limitations is we need a center tapped transformer for this. Next we are going to discuss about the bridge rectifier. 4 diodes, diode D1, D2, D3, D4 are connected in bridge manner, bridge configuration. Then here we are having an input side, then here we are having an transformer, then the bridge configuration, then followed by the load. So during the positive off cycle, the diode D1 and D3 will become forward bias. So through D1 and D3 the current will flow. So it just follows the inputs signal. Okay. Then during the negative off cycle, if you are looking towards the negative off cycle, that time D1 and D3 is in blacking state and D2 and D4 is in conduction state. Therefore, it follows the negative off cycle output. So here we are having an continuous output. During positive off cycle and negative off cycle, we are having an continuous output. If you look at the waveform, here we are having an input side. This is called positive off cycle and this is called positive off cycle. This is negative off cycle. During the positive off cycle, the diode D1 and D2 will conduct. D1, D2 conducts and the output is getting. During the negative off cycle, diode D3 and D4 as conducts and then we are having an output. So here another advantage is we doesn't need any center tap configuration, center tapped transformer, because the ripple factor is highly reduced. Next we are going to compare the performance parameters of half wave rectifier, full wave rectifier and the bridge rectifier. The first parameter is number of diodes. The number of diode requirements is in half wave rectifier is 1 and then center tapped configuration it is 2 and then in bridge configuration it is 4. Peak inverse voltage, the peak inverse voltage is Vm in case of half wave rectifier. In case of center tapped transformer 2 Vm. This is the one of the limitation, because PIV increases means the rating of the diode we need to increase. Rating of the PIV rating increases means the diode cost will become increased one. So this is one of the limitation in center tapped configuration, 2 Vm. Okay. Then in bridge configuration also Vm. maximum efficiency. The maximum efficiency of half wave rectifier is 40.6, and then in center tapped it is increased to 81.2, and in full bridge it is increased to 81.2. Then ripple factor, this is the main parameter, this is the main performance parameter. Ripple factor is 1.21, that means 121%. It is highly not recommended because there are so many ripples are present in the DC side. So 121% is not advisable. So we need to have a special filter arrangements. So it is highly not recommended. Half wave rectifier is highly not recommended. Then center tapped transformer, it will be reduced into 0.48, 48%. In case of output frequency, here half wave rectifier is F in, and then center tapped 2 F in, and then bridge full wave rectifier also 2 F in. Then average DC current Im by pi, 2 Im by pi, 2 Im by pi. From the comparison table, we clearly know half wave rectifier is highly not recommended. We may use the center tapped transformer, but only the limitation is we need to have the center tapped transformer, and then we need to have a peak inverse voltage of 2 Vm. So from the comparison table, it is clear the bridge rectifier is highly recommended. So thank you.